So if you've never been to psycode.org and clicked on Psi4Education in the upper right corner, that will take you to our Psi4Education website. And on the Psi4Education website, you can find all of our current labs. And I've just kind of summarized a few of our most popular labs here. So that if you haven't been to the website, you might be motivated to go look. I also want to use this slide to talk about sort of our two different types of labs that we have right now. So right now we have labs that use WebMO. And if you're not familiar with WebMO, WebMO is a standalone program. It's a graphical user interface that lets you build molecules and set up calculations for different quantum chemistry programs. And every individual quantum chemistry program has to actually provide the interface between WebMO and their code. So way back in 2008, as my students say, like in the olden times when you wrote on stone tablets and drove a Fred Flintstone car, in the olden times of 2008, I wrote the first Psi4 WebMO interface, and that kind of gave us our first graphical front end for Psi4. So some people are still using WebMO, and some people are using it very successfully, and our WebMO labs are very popular. So we're not really planning to get rid of them, even though we have our new Psi4 API labs. So a lot of our WebMO labs are designed for the general chemistry curriculum. There's one where you kind of talk about how do we define the size of an atom, and you look at the probability distribution for sort of different size isosurfaces, and the students really think about, since the electrons are not a defined position thing, how do we even define the size of an atom? There's another WebMO lab where you make electrostatic potential maps and you look at some different cation pi interactions and you think about what that has to do with binding energies. There's a lab where you take water and you look at the MOs as you stretch the OH bonds, and you kind of think about, when does water really go from being water to being an H plus and an OH minus, and how do you see that in the molecular orbitals? So that's one that we have. We have a very popular astrochemistry lab in WebMO where you calculate rotational constants, and then you kind of use those to identify molecules that you would see in space. And then we have a WebMO lab where you just build molecules and identify point groups, and it gives you a visual way to do that. So those are some of our most popular WebMO labs. And then since there's the Psi API, we now have all these labs. These are some of our newer labs that use the Psi API in the Jupyter Notebook. So we have a very popular lab about writing your own Hartree thought code. This is literally a vision I've had since I was a second-year faculty member, to somehow have students understand the iterative nature of the Hartree thought code, but not have to calculate all their own integrals. And that's really what this lab is about. It guides them through the Hartree thought procedure, and it actually has them write the code in the SCF iteration loop. One of our newest labs is our machine learning and computational chemistry lab. This is a wildly popular lab. Whenever anyone random gets in touch with me on Twitter because they found one of our labs and they think it's super exciting, it is always the machine learning and computational chemistry lab. Everybody wants to learn about machine learning, and we have, as best I can tell, the only education resource out there where students actually do machine learning in the activity. We have a lab about determining structure from microwave spectroscopy. So you use rotational constants to determine structure within the notebook. We have a new lab about intermolecular interactions in SAPT. And I'm not talking about these more because some of these contributors are here today and are going to give you lightning talks where they actually show you their Jupyter notebook so you can really see what this lab is about. We have one where you calculate spectroscopic constants from a calculated potential energy surface. And then we have one where you do basis set comparisons and you think about how that affects accuracy of calculations. So this is really the gist of the Psi website. Now I'm going to do something semi-dangerous, and I'm going to stop screen sharing there. And I'm going to actually pull up the website super briefly to show you what you can see about each lab. So I'm going to share screen again. Let me find Google Chrome. Here we go. So I think, what are we looking at? Are we now looking at the PsiCode website or no?
Yep.
Okay. So this is currently PsiCode.org. I know they're hoping to do a website update in the future, but this is what it looks like right now. And if you click right here on Psi4Education, you get to our webpage. So if you scroll down, there's information about getting started. There's a page that describes the prerequisite Python knowledge that you can assume when writing a lab. I'm going to go over that later. There's a little plug here for our partnership with ChemCompute. There's a paragraph describing how to get access to the instructor resources, which is something we'll talk about later. And then this is really what I wanted to show you is this is the lab activities. If you click on the title of any lab, then it takes you to a rendered Jupyter Notebook preview so that you can kind of see what's going on in the lab and get the basic idea. But this is, of course, not interactive. You're just looking at it. And then if you actually want the students to download these so that you can use them in class, you can just right-click and download themselves, and then you can post that on your learning management system. You can post that on your learning management system or just have the students directly download them themselves. And I believe I just had a problem with my headphones, so I hope everybody can still hear me. All right, so let me go back to the PowerPoint. That's not the PowerPoint. All right, let me go back to the PowerPoint. All right, I think we're back on the PowerPoint now. So that's just some of our most popular labs, and that's how you can access them. And then the other thing I wanted to talk about briefly is just sort of how our materials are organized. And when people mention some of these different GitHubs later, I kind of wanted to make sure we were all on the same page. So we have our website at psicode.org, which is just sort of a website. It's where people find out about us. As I showed you, there's a link to preview each lab on GitHub and a direct download link. There are two relevant GitHub repositories. There's our Psi4Education repository, and there's our Psi4Education instructor repository. The Psi4Education repository is our public repository. This is our front-facing repository that anyone can find on GitHub, and this is the repository that links to the website. So this only has the student versions of the labs because we don't want the completed code versions to be readily available on the internet. If you were contributing a new lab, you would not do anything with this repo. This is the public repo, so it only gets updated when there is a new lab activity. So you never submit anything to the Psi4Education repo. If you are going to become a contributor, then we will give you access to this Psi4Education instructor repo. And this is a private GitHub repo that contains all the instructor versions and all the student versions of all of the labs. And the instructor versions have all of the code completed. So a lot of people who join this repo are not necessarily going to become contributors. I mean, we hope they'll become contributors eventually, but a lot of people who become members of this repo are just faculty members who are going to use the labs and want to see the code completed version. So we have to add every individual as a collaborator on GitHub, and then if you were submitting a new lab, this is where you would submit it. And later in the day today, Dom is going to actually give us a talk going over the logistics of submitting a new lab to the Psi4Education instructor repo. Okay? So let's say that you're now kind of convinced and you're like, okay, Ashley, I do want to use these Psi4Education labs. Maybe I want to use some Webmo labs. Maybe I want to use some Psi API labs. You know, how do I set this up? What are the options for my students to actually run their labs? So if you're doing the Psi API labs and you're using the Jupyter Notebook, you have pretty much 3 options that we know about. Students can use their own machine. You can have them install Conda and install everything on their own machine. Like, that's a very common thing that students do. I like students to set things up on their own machine, even though you will probably spend a whole lab period helping them get started. Just because if you want them to take the skills that they learn and apply them in other situations, they really are more likely to use their Python skills again if they've set the environment up on their own computer. That I have found that to be true. One thing I will mention is if you are having students install Conda and install Psi4 on their own machines, it is actually very important that you create an environment for Psi4, a Conda environment, because the main Conda environment has gotten so bloated that Psi4 does not resolve with the main Conda environment. And this is kind of intermittent, like sometimes they'll, change the main Conda environment and it'll work, and then sometimes they'll change it and it won't work. So it is important that if you are going to have students use their own machines, that you have them create a Psi4 environment. If you're unfamiliar with the Binder product, I just wanted to make sure I mentioned Binder. Binder is a website. It is a core Jupyter product that creates Docker images from a GitHub repo. So if you have a GitHub repo and you put all the notebooks you want your students to be able to access, then you can use this Binder product to create a virtual machine, and then you'll be able to distribute that virtual machine just through a link. That virtual machine does have to build, and it can be very slow, and the more students you have using it, the slower it is. So Binder is really great if you're giving a quick demo, but it's not ideal for a large number of students. And then if you heard my talk on Thursday, you heard me mention our new partnership with ChemCompute. So ChemCompute, you can register for a free account at chemcompute.org, and you don't have to ask permission. You don't have to get an access pass for your students. Your students can just immediately sign up and use ChemCompute. So if students aren't going to use their own machines, or you aren't going to install things on your own computer lab, I would probably recommend ChemCompute for most people. As far as Webmo goes, if you want to use Webmo, you can set up your own Webmo server on your campus. This is what we've done at Cal Poly because we have about 1,000 students who use Webmo every quarter. And you can monitor the students' jobs, you can delete them, you can reorganize them, and if you want to leave the students' accounts active, they can use them beyond your class. Another option that a lot of people are doing who do not have the administrative support to have their own Webmo server is running Webmo in a cloud service. And Brandon is actually going to talk about this in just a few minutes, so I'm not going to elaborate on this a whole lot, but that is an option if you want to do some of those Webmo labs. So then the last thing I want to spend a couple minutes talking about is like I said, what are the considerations for writing a good Webmo, a good Psi4Education lab that is going to be popular? So on our website, we have a clearly defined list of Python prerequisite skills that we expect the students to have. And it's very important when you're writing a new lab that you remember that these are the only prerequisite skills that you can assume.
okay? But it's also important to remember that you can assume these prerequisite skills. So you don't have to explain every single thing in your lab activity. We do not offer resources to sort of help students develop these prerequisite skills because we think MOLSI, which if you're not familiar with MOLSI, that's the Molecular Sciences Software Institute. We think that they've done this better already. So MOLSI has this workshop called the Python Data and Scripting Workshop. And if you had your students do lessons 1, 4, and 5 of that Python data and scripting workshop, then they would develop all of these skills. And I know that some faculty just, MOLSI's materials, which I'm going to show you on the next slide, MOLSI's materials can be done as sort of self-paced workshops. So some people just send out the link to their students and tell them to do lessons 1, 4, and 5. Some people who are going to use this a lot in their class, they actually devote a class period to going over these 3 lessons. For completely novice programmers, going over these 3 lessons probably takes about 2.5 hours. So you could probably fit them into sort of one class period if you had a traditional 3-hour lab structure. And these lessons are already fully self-contained. They teach something, they give the students an exercise to do, they have a summative assessment at the end of each lesson. They're really, really well done, and they've been used to teach thousands of students Python already. So if you, the MOLSI education website is education.molsi.org/resources. And when I'm not screen sharing, I will paste this into the chat so that everyone can bookmark this. Their hallmark training is the Python data and scripting workshop. That's the one I was mentioning on the previous slide, that if you did lessons 1, 4, and 5, you would have all of those prerequisite skills. And then there's another MOLSI workshop called the Quantum Mechanical Tools Workshop, which if you really wanted your students to develop some real prerequisite skills before they started going into your class, the Quantum Mechanical Tools Workshop teaches them how to do geometry optimizations, potential energy surface scans, and several other types of quantum chemistry calculations. And it teaches them to do them in Psi4. So these are resources from MOLSI that you can utilize when you are trying to get your students started with Psi4Education. Okay. So finally, I just wanted to say, what makes a good lab? What are the features of our popular Psi4Education labs? And the number one thing that I would tell you to remember if you're writing a new lab is to make sure that you keep the focus firmly on chemistry. Make sure that you're always focused on whatever the learning objectives of your class are. And if you're really trying to get the students to learn how to tell if molecules are polar and or non-polar, make sure that that's the focus, and make sure that that focus doesn't get lost in the programming or in the using Psi4. And what I always recommend is that people think about what they want their students to be able to do at the end of the lab activity. And I sort of write that summative assessment first, and then I back it up to make sure that the notebook helps them develop the skills that they would need to complete that summative assessment that I want them to be able to do. So always think about your learning objectives first and make sure that you focus on the chemistry. Most of the notebooks basically use the structure that they demonstrate a calculation type, and then they have the students do that calculation type on their own. Clearly, you're not going to be able to just give students a blank notebook and tell them to calculate a potential energy surface. You're going to have to give them some context for that. So in the demo notebook that I'm not showing today, for example, I show you how to calculate the interaction energy for a helium dimer, for 2 heliums. And I do it at one particular distance. And then I give it as an exercise to you to think about how to put that piece of code into a for loop, and do it for many different internuclear separations. So that's generally what most people do, is they demonstrate a calculation type and then they have the students do that on their own. Again, I want to emphasize the importance of being familiar with the Python prerequisites, and anytime you can reinforce those, you should do it. So if there's any point in time where it makes sense for them to make a graph during their lab, you should tell them to do it. You shouldn't make a graph to show them. You should have them make that graph, because that's a Python prerequisite skill that you want to reinforce whenever that you can. Similarly, anything you want them to do that is not on that list of Python prerequisite skills, you have to explicitly teach them in the lab. So if you're going to have them use a dictionary and then access elements of that dictionary, that's something that you need to explain to them in the lab. If you're going to have them use einsum from NumPy, you have to tell them, now we're going to use a function called einsum from NumPy, and this is how einsum works, and this is the inputs that it takes in, and this is why we're interested in this function in the context of our code. And you really need to put that in a detailed way, or the students won't be able to sort of self-pace through the lab. And then finally, the thing I wanted to end on is that a Psi4Education lab is always an activity. It is not simply a demonstration. What we have found is that most people who use Psi4Education labs teach undergraduate students. That's not to say that you couldn't use them for graduate students, but most of our users teach undergraduate students, and they are using these in curricular courses. So they need the students to do something that they can grade. So Psi4NumPy, for example, has this amazing library of tutorials, but those tutorials usually just explain how the code works and sort of shows you the inner workings of Psi4 and really teaches you the theory of the code. Psi4Education labs, on the other hand, you cannot just explain something. You have to give the students something to do. There have to be code portions that the students write themselves that reinforce the coding learning objectives and the chemistry learning objectives. So always keep that in mind when you're thinking about your lab design.